Hello, we are Team One, and for our ME452 interim presentation, we will be discussing the analysis and redesign of a manual pasta machine. For the product overview about the pasta maker itself, the manual pasta maker machine can make high quality pasta. It's portable and easy to use. We can enjoy different pasta textures with it, and it can also be used for different foods such as dumplings, pita bread, or even Asian noodles. Going into some of the design features here, our manual pasta maker uses different cutters or rollers to customize the pasta thickness and width. We utilize a hand crank to manually slide or move the pasta. Ours has a total of 62 components, which is broken down into 10 broader components or parts as shown on the right. We're estimating a total production volume of around 100,000 units per year. And going into our customer group, this amount is important as our primary customer group is restaurant owners. We have over 75,000 Italian restaurants in the United States, which yield around $54 billion. But our secondary customer group is also important as family, households, or cook hobbyists have been increasing in number due to COVID and DIY cooking at home and wanting to provide fresher meals for their families. Going into more of the important details here, with the fast diagram, we can see that to make pasta our main function, we go through a slew of steps, and our manual pasta machine actually covers 3 of the 4 required primary subfunctives. Going into our function component mapping matrix here, we connect the 10 broader parts that we broke down earlier to the terminal subfunctives that we completed in the fast diagram. From this table, we can see that the clamp covers only 1 terminal subfunctive, while the bottom piece actually covers 4. And we can also see that the prevent clogging subfunctive is covered by 4 different parts, while the cutting of pasta is only covered by 1, the cutters. Here's shown as a blown up view of the labeled parts again, with the 10 broader parts we broke them into from the original 62 components.
Here are 2 proposed sequences of assembly of pasta maker. Each sequence has 2 large sub-assemblies which include roller and cutter attachment. In the first sequence, sub-assembly parts are separately made and is being attached to the main frame. In the second sequence, the parts are built from the main frame one by one. This is an illustration of how 2 sequences are made differently. In the first sequence, sub-assembly can be assembled in Z-axis, which allows easier assembly. Here is the result of assembly sequence analysis. The ease of handling and locating parts will likely be similar as the parts are small and has a light weight. For the first sequence, I can make a separate location to make sub-assemblies, and in this case, I'll give higher credit because there will be fewer parts on the table, but this will require additional working space. Fastening in the second sequence can be easier because the parts are well grounded. Each sub-assembly can be tested individually for the first sequence, and this can be good in terms of quality standpoint as well. The analysis proves that sequence number 1 is more advantageous to assemble at pasta maker.
For the product family design, the main functionality difference for the 2 customers would be the pasta textures and whether they would be using the same location for the pasta machine. For the primary customer, he would need different pasta textures to serve his needs, and he would be okay with using it at the same location. Whereas the secondary customer would be okay with a single pasta texture but wouldn't be using the pasta machine at a single location. So for the component differentiation, there would be 2 main different parts. One would be the clamp, which would be used for the secondary customer but not for the primary, and second would be the multiple cutter profiles that would be present for the primary customer but not for the secondary.
Here, you can see the differences between the primary and the secondary variants. The main differences being that the primary variant should be able to make more kinds of pasta while not being expected to be moved around as much. As such, you can see that the primary variant has multiple cutter profiles that allow for different kinds of pasta to be made, while the secondary only has 1 profile. We're also considering allowing the secondary customer to modularly switch with different detachable profiles, which would require a different cover for the cutters. The secondary variant also has a clamp to allow for the device to be fixed and removed with ease, while the primary customer can be expected to maintain the device fixed in place for bulk usage. This is the assembly diagram for the first assembly sequence discussed. The blue represents the components for the primary variant, whereas the red stands for the secondary. The 2 main differences in the design being the lack of a clamp for the primary variant, as well as the separate cutter design and potential cutter cover design for the secondary variant. In order to improve this assembly diagram, we tried to maximize the delayed differentiation by waiting until the very end before incorporating parts for different variants. In particular, The cutters and accompanying cover were delayed to the end of the assembly, which means that assembly is now uniform until absolutely necessary, and so no parts are redundantly distributed.
Here is the bill of materials that show the corresponding price to each individual part along with the total cost. We made several assumptions here. We first assumed we produced 1,000 units annually. Tools had a useful life equal to the number of production units. Labor cost was around $15 an hour. Tooling cost for machining is a non-productive cost. And some of the items such as nuts, bolts, and gears were bought off the shelf at retail price. This was seen as a more cost-effective method, and we put those corresponding prices in the material cost column. The final product came to around $87.95.